In Episode 61, Support Business Continuity and Disaster Recovery Objectives, we focus on the idea that critical services must stay available even when normal conditions disappear. Business continuity and disaster recovery translate directly into an organization's ability to keep processing payments, protecting data, and honoring commitments while dealing with outages, incidents, or large-scale disruptions. For an exam, this is not an abstract resilience story. It is about keeping cardholder data flows secure, timely, and trustworthy when systems are stressed. The most effective programs rely on planned and practiced recovery actions rather than improvisation when something breaks. When continuity and recovery are embedded into normal planning instead of treated as side projects, the organization is far less likely to be surprised when a disruptive event arrives. A credible continuity and recovery program starts with knowing exactly which services matter most and what they depend on underneath. Teams identify critical business services such as payment authorization, settlement, reconciliation, fraud detection, and customer self-service portals, then trace each one down through applications, platforms, and infrastructure. That analysis includes upstream and downstream dependencies, including identity services, logging, monitoring, and external payment gateways that support those functions. Maximum tolerable downtime is then defined for each critical service, in plain language that business leaders can evaluate and refine. By capturing these tolerances in a structured impact view, the organization gains a clear understanding of which services require rapid restoration and which can wait without unacceptable harm. From those business-driven definitions, teams derive recovery time objectives and recovery point objectives, often abbreviated as RTO and RPO, and secure explicit agreement from stakeholders who own the risk. The recovery time objective describes how quickly a service must be restored after a disruption before financial, regulatory, or reputational damage becomes unacceptable. The recovery point objective describes how much data loss, expressed as time, can be tolerated without breaking commitments or losing critical information. A real-time payment system may demand near-zero data loss and very short recovery times, while an internal reporting database may accept longer delays and more rework. When RTO and RPO values are documented, approved, and tied directly to business impacts, they become practical design targets instead of vague aspirations. With recovery objectives in place, organizations map critical functions to alternate sites, cloud regions, and failover strategies that can realistically meet those targets. Some services may use active-active architectures, where traffic is distributed across multiple regions and can continue even if one region fails. Others may depend on warm standby environments that are kept partially ready and can be promoted within the agreed recovery time. The mapping should clearly show where each component lives in steady state, where it can run in a degraded or emergency mode, and how traffic or workload will move during a failover. When these maps are understandable to both engineers and business leaders, they provide shared confidence that continuity designs are not just theoretical diagrams, but actionable routes to keep services running. Designing for continuity also requires a hard look at single points of failure that could undermine even the most elegant architecture. A lone database instance, a single identity server, a shared storage array, or an unsupported custom script can each become the one component that stops recovery when it fails. Resilient mitigations might include clustering critical devices, replicating databases across zones or regions, and replacing one-off scripts with supported automation that has multiple maintainers. Human single points of failure, such as a single specialist with unique knowledge of a key system, need attention as well through documentation, cross-training, and shared access models. By deliberately identifying and reducing these single points of failure, organizations turn fragile chains of dependency into more resilient systems that tolerate individual faults. Backups form the backbone of any disaster recovery capability, but simply creating copies of data is not enough. Immutability features prevent backups from being altered or deleted by attackers, especially important when dealing with ransomware or insider threats. Logical and physical isolation, such as offline copies or backups in separate administrative domains, reduces the chance that a compromise of production systems will spread to backup repositories. When backup protection is combined with clear, rehearsed restoration procedures, the organization gains practical options for recovering systems even from severe destructive events. Technology alone cannot carry the full load during prolonged outages, so documented manual workarounds for essential processes are a critical part of continuity. For example, a contact center may temporarily switch to limited, strictly controlled offline capture of sensitive data using predefined forms and secure storage procedures when online systems are unavailable. Finance teams might follow a manual reconciliation routine based on daily export files or offline logs, while automated jobs are offline, with clear instructions on how to merge those records once systems are restored. Security and compliance requirements still apply, so these workarounds must be designed, risk-assessed, and approved ahead of time rather than invented during a crisis. When staff are trained on these documented alternatives, the business can continue delivering essential outcomes even when technology is constrained. Restoring services after a disruption is most effective when it follows an intentional and well-understood sequence that respects technical dependencies. In many environments, identity services and directories must be restored first, because almost every administrative and application action depends on working authentication. Networking and connectivity follow closely, including routing, firewalls, and secure remote access, to ensure that teams can reach the systems they need to repair and validate. Data platforms, such as databases, storage systems, and messaging layers, usually come next, since business applications cannot function without consistent and available data. Only when these foundations are stable does it make sense to bring application tiers and external interfaces back online, gradually opening the door to customers and partners while monitoring performance and risk. Planning alone does not create resilience, so organizations use tabletop exercises to rehearse scenarios, decisions, and communications under controlled conditions. A tabletop exercise walks a cross-functional group through a narrative, such as a regional cloud outage, a major data center fire, or a widespread ransomware incident, step by step. Participants discuss what they would do at each stage, who would make key decisions, how they would communicate with customers and regulators, and which recovery options they would choose. Observers capture gaps in the plan, unclear roles, missing contact information, and decision points where authority is ambiguous. Over time, repeating these exercises with varied scenarios builds shared understanding and confidence, reducing hesitation when a real incident demands quick but well-informed choices. Beyond tabletop rehearsals, full restore tests provide the hard evidence that backups and recovery procedures work as designed. A meaningful full restore test does more than validate that data can be read from media. It restores an application or environment into a clean state and measures how long the process takes. Teams monitor for errors, configuration mismatches, and security control gaps that appear in the restored environment, such as missing patches, missing logging, or disabled monitoring. Attention is also paid to user experience, including how quickly staff can resume their normal tasks and how much rework is required. When restore tests are run regularly and their results are documented, they provide strong assurance that the organization can actually meet its declared recovery time and recovery point objectives. Continuity planning extends beyond internal systems to include supplier and service provider dependencies, many of which are critical to payment processing and security controls. Organizations seek clear continuity assurances from key suppliers, including data centers, cloud platforms, payment gateways, and managed security service providers. Contracts may include specific recovery commitments, such as maximum outage durations, data retention guarantees, and notification timelines when incidents occur. These commitments should be transparent and aligned with the organization's own continuity targets. Otherwise, a supplier's weaker position can become the organization's hidden risk. By integrating supplier continuity information into impact analyses and recovery plans, organizations avoid the trap of assuming that external parties will simply handle it during a crisis. After any exercise, incident, or significant change, capturing lessons and updating continuity artifacts promptly is where real improvement happens. Teams review what went well and where delays, confusion, or technical issues occurred, and they translate those observations into concrete updates to plans, procedures, and training materials. Contact lists, escalation paths, environment inventories, and recovery runbooks are refreshed so that they reflect the current reality rather than last year's architecture. Evidence repositories, including logs of exercises, test reports, approvals, and remediation tickets, are updated so that assessors can see a clear story of continual refinement. By treating lessons learned as inputs to a living program rather than as a simple meeting deliverable, organizations maintain continuity capabilities that evolve along with their environments. Before closing, it is useful to pause for a brief mental review of the major building blocks in this continuity and recovery story. Objectives define what must be achieved in terms of availability and data integrity, and dependencies reveal what each critical service relies on. Backups, protected by encryption, immutability, and isolation, sit ready to support restoration when systems are damaged or compromised. Testing through tabletop exercises and full restores shows whether plans are realistic and whether people, processes, and technology can perform under pressure. Supplier continuity commitments and structured lessons learned keep the entire system, internal and external, moving towards stronger and more reliable performance over time. The practical outcome of supporting business continuity and disaster recovery objectives is a program that does more than satisfy a checklist. It gives leaders credible confidence that essential services will survive disruption. For someone in a security role, that means being able to explain how payment processing, cardholder data protection, and supporting controls will continue even when improbable events become reality. A natural next step for any organization is to schedule a realistic restore drill for a representative payment-related service and to validate that backup integrity, restoration procedures, and recovery times all align with documented objectives. The evidence gathered from that drill can then feed back into updated plans, designs, and agreements. Over time, this cycle of planning, exercising, restoring, and improving becomes the foundation of a continuity culture that treats resilience as part of everyday governance rather than a one-time project. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.